In a world where data science holds the key to addressing humanity's most challenging issues, the Data Science Without Borders DSWB initiative has emerged as a bridge across Africa and beyond, linking countries to opportunities that would help governments harness the power of data for positive change.
Data Science Without Borders, starting from its name, is a very interesting project. I'm the lead with a couple of colleagues from very many partnering institutions. It's a dream that we wanted to see data science spread across Africa. We always know that Africa has been known to lag behind the Industrial Revolution, but with the advent of AI and data science, we wanted a project that will bring partners in the African continent. We'll look at institutions coming together to start to harness the power of this new technology, to leverage their data sets, and to build capacity in data science and AI to help Africa realize its dreams through data.
Launched in February 2024, DSWB continues to empower African scientists to champion data-driven solutions. By breaking barriers and strengthening systems, DSWB is driving innovation and creating lasting impact across Africa.
Many times it's been said Africa needs to leapfrog. Yes, we need to leapfrog. We need to catch up with AI. We shouldn't be left behind, but we need to fix the processes that will get us there. Look for the data. Where is it? Is it in good quality? Do we have the people who are going to mine this data, analyze the data? Do they have the skill sets? Do we have the infrastructure to actually do the analysis and punch all these analyses out there? And of course, the governance. You know that Africa has a lot of data governance diversity. How do we get to that point? How do we learn from the different countries? And once we fix these important pillars, even as we leapfrog, it will be the success for effective use of data science and AI in Africa.
With passion, commitment, and collaboration, we can continue building a future where borders do not limit progress and where data science empowers us all.
Thank you very much, Nisita. Thank you. It's good to be here. I don't know where most of you are joining from, but I'm from Kenya and I'm joining from Barcelona. And I just want to cover put a caveat on this first. It's that I have a hard stop at the end of the hour, so I hope I can do everything within the remaining time. And I've tried to adjust my content based on that. And hopefully that will be enough time to do that. So if you'd allow me, I would like to share my screen and produce and proceed with this. I hope you can all see my screen somehow.
Yes, I can see.
Okay, awesome. So yeah, like you said, my name is Albert. I'm AI researcher, engineer, depending on which day and who you're asking. Nowadays, it's kind of hard to know what the line is between the research and the engineering and all that kind of thing. I want to make a couple of disclaimers again before I proceed on this workshop. So first of all, I'm representing myself here. I am not here on behalf of my employer or any other affiliations that I have. I'm purely here as a scientist, as a researcher, as an engineer, and to give my thoughts, primarily my own thoughts, and based on my experiences working in AI for the last couple of years, and also my scientific input to the discussion of reproducibility. It's something I encounter from time to time. So a lot of that is my own views, my own opinions, and my own scientific opinions, let's say. Also, another disclaimer is I'm a very, very bad slide maker, so please don't make fun of my slides. I don't do well with making slides. My slides tend to be too bald, I've been told. But hopefully, I hope you can listen to me and not just look at my screen. There, my slides. Those slides are mostly for me to guide me in my talk. So just try to listen to me and not focus so much on how bad my slides are. Um, so yeah, with that said, thank you very much. Let's get started. So reproducibility in the age of AI. When I think when I was approached to give this talk, I thought, oh my goodness, this is so complicated, and there are so many angles to this, and I don't know how we can go about it. But then because AI is applied to so many things nowadays, and so for some things it's reproducibility is very, very relevant, and for some things it's not. It's okay. You can do with or without it because of the nature of the systems. And it kind of got me thinking about my background and where I started and all that kind of thing. So when I was in my master's, I was doing a lot of research around fault tolerance. And the idea behind fault tolerance was to see how often a system can tolerate faults, how it can fail, what kind of failures there are. And these are computing system, let's say, like a CPU or a much larger complicated system. And in that, during that study, there were levels to this, right? There are some failures that we call them silent failures. They happen. You don't really worry too much because they don't affect the system. But there are failures that are called critical failures, and those ones affect the system. That was one thing. And then the other thing, there was also the problem of the application. So when a system failed, depending on the application, that meant that the way you design the system was quite important, right? So to give you an example, if your CPU fails or one bit in your CPU flips or something like that, which kind of like errors we were looking at, and you're just typing Microsoft Word document or browsing the internet, it's not really a big problem, right? It's you can live with that, right? You can even if it completely fails, you can restart your computer, you can start again. And so that was like, so based on the application, that's tolerable or may not be tolerable and whatnot. But then if your system or if even a single bit flip happened, and this is the system that flies your Boeing 737 or your Airbus A320, that was quite a mess. So that was very, very critical. Those are we call critical systems. No, I'm not yet moving my slides. Don't worry. I'm still on my background. And so those things varied from one to another depending on where you're dealing with. So in airplanes or in rockets and these kind of things, we had to ensure that the system was designed in such a way that it could tolerate a lot of failures, right? It had like multiple redundancies and whatnot. Like in a classic airplane, there are over like 4 levels or 7 levels of redundancy for every process that needs to happen. And so yeah, I'm coming from that. And so why am I telling you this story of fault tolerance and my earlier work in my PhD and whatnot? Because I see a lot of that in what we call deterministic systems now, and that's where I'm going into the idea of AI, right? So if I execute an equation, ideally I want to have the exact same answer, even if I execute it 10 times, right? That's kind of like how you want things to be. If you execute that and get different answers every time, it matters, right? To some degree, you can tolerate that. To another degree, you cannot tolerate that. And I want to go with that information now slowly to the discussion that I'm about to have. So a little bit about my background. Like I said earlier, I'm an AI engineer working at the intersection of AI, data, and infrastructure. A lot of my PhD work was around infrastructure, high performance computing, and that kind of thing. So I did a lot of distributed systems, scientific computing, and a lot of large scale AI workflows. And during that time, most of my work was around building and evaluating real world AI systems. And part of that was ensuring reproducibility, data quality, and systems integrity. And I will briefly show you why. So a lot of this was at the hardware level, at the systems level, and that kind of thing. But it was quite important also when you went a little bit up. So when I started, when I was doing, during my PhD, reproducibility was largely framed as an engineering problem, right? So, and I put this image, this diagram here. It's a picture from one of my papers during my PhD, It's because we wanted to do a whole lot of things. Some things like deterministic checkpointing. We wanted to run an AI workflow end to end. During as it's running, we're checkpointing, and we want to make sure that if we checkpoint these 4 or 5 times, we get the same results and whatnot. The other thing we were doing was a lot of distributed training, right? So if you have let's say a model like this one, you break this model into the first node, the second node, and the third node, and the fourth node, or what we call like model parallelism, right? And the reason you're doing this is because the model is too large to fit into one GPU and whatnot. And this was really complicated because if I execute this training with the GPUs, with the model split in 4 GPUs, I need to make sure that I get exactly the same results as I would get in training it on a single GPU, right? Like when I'm doing my splitting, when I'm doing my all the engineering that I need to do for this model to fit into the 4 GPUs, I needed to make sure that I did not introduce any changes from the original ones, right? So this model needed to run exactly as it would run in a single GPU. And my supervisor was very, very strict on it. He said, we cannot reproduce it, we cannot publish that paper, it's meaningless. Because if you're training, and I would have all these excuses and tell him like, yeah, but it's AI, the training will take care of that because it will, cancel out and all those kind of things. But he was very, very adamant. I was like, we have to get exactly the same results if we do it in one way or another way, because mathematically it should be the same. And if we cannot get the same result, then this is not science. We are not doing anything here. And that was a very, very sort of formative time of my career and my journey as a scientist. I learned the hard way that reproducibility was so essential in the scientific works we were doing. And that drives me now to the topic we want to cover today, reproducibility in the age of AI. And another disclaimer here is that a lot of my talk is going to be focused on the usage of AI for science, right? Right now we're having AI being used to run scientific experiments, do a lot of things. And that's, for me, where this idea of reproducibility becomes very, very important. So that's kind of where I'm coming from. That's the background I have. And this is what I saw reproducibility firsthand. This is how I experienced reproducibility firsthand. I learned that in science, we need to be able to reproduce things. We need to be able to come up with experiments that can be reproduced. Otherwise, there is no scientific integrity and all that. So the goal was ideally to reconstruct the exact state of the system at any given point. Now, we are using AI to do experiments. We are using AI to conduct research and to do a lot of things. But we know that inherently, AI and a lot of these models are not deterministic. And that raises a lot of challenges, raises a lot of questions on how we proceed moving forward. So in the next 20 to 30 minutes or so, I will share with you my thoughts around this, what I think we can do, what I think the problem is, and what I think the application of AI in science, or the application of AI in these critical domains. Remember, I started by telling you that domains matter, right? If you're using AI to do something else, might not necessarily be as important to reproduce as when you're using AI to conduct an experiment that will then be put in a human body or put in a plane or that kind of thing, right? So there are levels of this, and the domain matters. And I want us to go forward with that in mind. So here we are, me as an engineering student looking at reproducibility as an engineering problem. What engineering taught me, and during those years, and thanks a lot to my supervisor, was that if you cannot reproduce a system's state, you cannot debug it properly, you cannot know what's going on, you cannot trust it, and you cannot deploy it. And he was very adamant on this. So he said, reproducibility, it's not an option, it's a requirement for success. That's from a scientific perspective and the work we were doing and all that. So I learned a lot of these lessons from science. And if I look, I'm not a biologist, I'm not a, how do you call it, lab scientist. I don't go to the lab, I don't do experiments. I mostly do a lot of my work on my computer. But from what I know is that the classical view of reproducibility in science is that you have the same experiment, the same data, the same method, you should ideally end up with the same thing, right? The underlying assumption is that you have a controlled environment, you have stable systems, and you have a fully specified methodology, right? In practice, this usually means methods are very clearly documented. I'm going to take this sample, I will do this, I will do this, and then I will do that. And for this reason, results can be independently verified. If 2, 3, 4 scientists do the same experiment, ideally we want to come up with the same results, right? Or at least an explainable variance, right? You can have some variability, but it's bounded within some constraint, and we can have some sort of an explanation for what this means, right? So that's the classical view of science. With AI, things change a lot, right? You want to use AI to do your experiment, you want to use AI to do science. Things change a lot. Why? Because AI systems introduce a bunch of things that get really, really messy very quickly. First of all, a lot of these systems are not deterministic by default, right? You can ask, and you can do this. You can ask ChatGPT a question, ask it exactly that question the next time, it's going to give you a different answer, or that varying. Or you ask 2 different models, you're going to get totally different answers. The underlying idea is still very, very similar, but you're going to get different things. The other challenge with AI, and especially when you're using it in science, is that there are these very, very large scale pipelines. A pipeline to do this, a pipeline to do this, a pipeline to do that, and whatnot. And then it also heavily depends on the data, right? The data that you have, the data that the model was trained on, and all that kind of thing. And then it also has these very complicated model architectures that are so hard sometimes to verify and to know what's going on inside the models themselves. So with this given, with this phenomena, the same inputs do not always produce the same outputs, right? You can have a variance here. And so you can conduct an experiment with AI, you can do an analysis with AI and end up with 2 different sets of results. So if you look at this, this architecture or this paradigm, there's so many levels of complication that could arise from any of these pots that we have, right? So AI changes a lot in terms of how we do experiments and how we do science, and eventually the behavior and how we should look at science from an AI perspective. And by the way, I know when some of you joined this webinar, I should have clarified that at the beginning. You probably expected me to talk a lot about the the ethics and kind of like the AI reproducibility aspect of things, because that's sort of like that domain. But I'm giving a lot of perspective from engineering and from science as a user of AI, right? As a user of AI, what that means and how that plays into our world. All right, so this is what happens when we now try to use AI for experiment. So there's a big shift here, right? We have moved from experiments in the lab to and these experiments are most of the time very controlled, very repeatable. We can do exactly the same thing and whatnot. To now a bit more of a complicated system here, where we have these pipelines to do so many different things. And by pipelines, we're just talking about like AI or machine learning pipelines that we design with some workflows and that kind of thing. Also, it's very multi-step. Like you say, there's data pre-processing, pre-training, and a bunch of other things that are introduced into the whole thing before you can come up with the results. It's very distributed, right? It could be data was collected elsewhere, this was trained elsewhere, we're using a model from someone else, and all that kind of thing. And also, even in the computing system itself, it could be it's being trained probably in a distributed environment. It's very data-driven. And it's complex and always evolving, right? The rate at which AI is evolving and changing is just insanely high, right? So we have all these challenges that are introduced by AI when we want to do our work, when we want to use AI for healthcare, for critical systems, for agriculture, and all these kind of things. So now reproducibility is not just something you're trying to do in your lab, it spans across the entire systems. You have these very, very complicated systems. And now you need to kind of think about reproducibility in all those aspects. So today, reproducibility actually means something else, right? We can produce results a lot faster but we can't validate them at the same speeds, right? So we have more results in a scientific experiment or in our work, and we have less certainty, right? We are producing an enormous amount of results, an enormous amount of data, than we can verify them. So the cost of experimentation is, of course, very, very low, but it increases the cost of verification. And I want to give a very stupid example here. If you're a journalist and you want to write an article about something, I don't know, let's say malaria in Kenya or whatever topic you want to pick, it's so easy. It would literally take you about 5-10 minutes to write that essay, a really good essay with ChatGPT, right? Or any other of those tools. The problem is journalism is one of those domains where verification is really, really important, right? Facts are so important. When you do that essay with your ChatGPT, you don't have time to go to the ground to talk to people in the hospitals to verify the number of cases they have, the kind of information they have firsthand, and whatnot. So you really cannot redo that, right? What do you end up with? You end up with a lot of results. Like you can write a ton load of articles as fast as you want, but you really cannot verify a lot of that information, right? And this is just a very basic example to show you what this means in the real world. Imagine now for that same thing, not a journalist, to replace a journalist with a scientist who is conducting a very important experiment on a particular topic that is critical to, say, human life or safety and that kind of thing. So yes, the cost of experimentation is drastically low. You only need 10 euros to subscribe to ChatGPT and write as many articles as you want. But there's a lot of complexity in verification, right? ChatGPT will spit out numbers, it will hallucinate, and all that kind of thing. So reproducibility, therefore, today means, can you reconstruct the entire workflow that generated that result, right? It's not just rerunning that code. Can you go from data collection to the final result and reconstruct that? The problem is, and this is where the challenge is, and this is the challenge of reproducibility today, is that this process is not trivial. Most of the time, we're using just one part of a workflow, not the entire part. We have very, very little visibility on the other parts of the workflow. The other problem is that it's not cheap either, right? It's insanely expensive to reproduce some of these models or to reproduce some of this work. Even if we are the scientists designing this, the tools for reproducibility are expensive. It takes more engineers. You have to do more work to be able to write or to create an AI system that can be reproduced, right? And that comes the challenge with what we understand as the meaning of reproducibility today. So why is this critical and why is this such a big problem? It's because of how the AI research flow looks like. If you're developing AI systems or building systems that will be used for healthcare or critical systems of this kind of things, this is the challenge you have. You have a very sophisticated workflow, and each layer in this workflow must be traceable. You must be somehow able to reproduce it. So it depends on the data, right? Can you reproduce the data? Do you have exactly the same data? It depends on the code. This is easy to reproduce, at least. It depends with the model, right? When you train a model, it's not the same thing. It depends with the inference. And also it depends with the evaluation, right? How do you evaluate that model? How do you benchmark that model and all this kind of thing? So this whole AI research workflow introduces a lot of complexity, which then, as I said earlier, makes reproducibility extremely challenging and extremely expensive task. That being said, even before I go to the next part, we have to think about reproducibility and we have to be very intentional about how we can do it. And so in the next couple of slides, I am going to share some of the places where reproducibility breaks, right? In the whole of this workflow, from data, code, model, inference, and evaluation, where reproducibility breaks, and now to slowly start thinking about how that can be fixed and how that can be solved. So if you look at data, a lot of time we don't have data versioning. And I've been involved a lot in data creation across Africa with many people trying to create new data sets that are going to be used for AI and all that kind of thing. And one of the things we were very critical on when it comes to data creation was this idea of versioning, right? When you have data, then it should be probably, it should be properly versioned. You should be able to know this was the version, this was the change in the version, this is what was introduced and whatnot. That's step one. Step two, it should be very, very clear what was the pre-processing that was done on this particular data, right? This has to be documented somewhere, right? In step one, we dropped these values because of this and this and this, right? So it becomes very, very clear. And then there needs to be some sort of preference. Where did it come from? Who changed it? Who accessed it? Who touched what, right? So these are all the places where reproducibility can break. If you don't have correct versioning, then you cannot reproduce that data because you don't really know what happened in the previous version. If your pre-processing steps are changing and they're not documented, then you can't really know what happened in the other steps and so on and forth, right? So this is at the data level, right? Just to mention it, we will think about it a bit later. And then we come to the model now, right? If you don't know much about the training data, which we just talked about earlier, then you have this data opacity, right? You can't really know what was used where and why and all that kind of thing, because the training process might not have been really well documented. And this is, by the way, obvious in now with the emergence of large language models. There's a lot of debate and a lot of discussion that is going on around making this very clear, right? Whenever even open source models, and this is not a conversation about open source, but even in open source models, more and more now, we are seeing the community and the scientists and a lot of people say, hey, when this is an open source model, yes, give us the open source model, but also give us the data that was used to train this open source model. Let's see exactly what it was, what it entailed, and whatnot. Because that is how we can be able to see the biases we are seeing here, the issues we are seeing here are coming from this particular data, and this is the problem, right? So at a model level, that's what. The other thing is model updates. These models are continuously being updated. We have new versions coming up. We have a lot of changes, but we don't really get to know what changed in version 1 and version 2 and version 3 and whatnot, right? Was it more training data that was provided? Were there, more training time that was given? And this happens a lot with even the publicly available AI systems that we use, your ChatGPT's, Gemini, and whatnot. And so this brings about the issue of, lack of versioning and whatnot. At the inference level, it also becomes extremely hard to break. I mean, it becomes extremely easy to break reproducibility. Why? The prompts you give are not necessarily the same prompts you give every other time. We don't have a very sort of scientific methodology on how we should prompt system. Everybody does it their own way, right? Yes, there has been talks about like standardizing this, and this is how you should do good prompts and whatnot. But really, that's very, very unclear. And because of that reason, you end up with very, non-deterministic outputs, right? And the other issue with this inference is this API instability. So when we go now again to the evaluation level, right? So I've talked about data, model, inference, and now let's look at evaluation. This is now when you want to benchmark your model and all that kind of thing. First of all, the metrics to use for benchmarking are not also standard. That's another part where the reproducibility breaks. The benchmarks are not standard. Everybody is benchmarking it with their own way and their own benchmarks and whatnot. Again, by the way, there is really good progress on the benchmarking front now. There's so many good benchmarks out there, but they benchmark different things. And the interesting thing also is that a lot of these benchmarks are not culturally inclusive, let's say. So if you benchmark a particular model in another language versus if you benchmark it, say, in Kiswahili or Kinyarwanda or something like that, again, there is not very standardized, like the benchmarking has not been standardized across that set of variables and whatnot, which kind of brings me to the other topic, which is the experimental setup, right? So the way you do we benchmark this by doing this and this, like this is the process we use to set up the benchmark and whatnot. If there is no standard for that, then reproducibility breaks. So the real problem though with reproducibility is that it doesn't fail just because systems are complex and all that. Yes, the systems are definitely complex. We can't reproduce every part of that system, and I will talk about that later. But reproducibility, and this is the key takeaway from this talk, if you get anything from me, this is the key takeaway. Reproducibility, it fails because decisions across the pipelines are not very well documented, right? And that's why I said earlier, I think reproducibility is an engineering problem. And I will show you why I think it's an engineering problem. So data selection and filtering, if this process is not very well documented, if it's not very clear, then you cannot reproduce that. Pre-processing steps, model choices and configurations, what model, what were the configurations, what were the decisions for that particular configuration, and all that, again, needs to be very, very well documented if at all we're going to use AI for important systems. The prompt design and inference settings also need to be very clear and very documented, right? This is how you introduce to a certain level at minimum some level of reproducibility, right? And then the evaluation setup and the metrics, right? So basically what I'm trying to say here is that what cannot be recorded cannot be reproduced. If I told you today to make me, and I'm trying to remember my high school chemistry here, which was terrible, by the way, but if there is a process to come up with a particular acid, let's say, and I tell you, a new person in the lab, that, here, I made this acid, I want you to remake it. If you clearly documented the process, everything that was involved, we heat this to this temperature, we add this here at this particular time and everything, and that process is really well documented, then we stand a chance of reproducing it. So what I'm arguing and what I'm advocating for, or my view here, is that those same principles that we had in physical sciences, those same principles that we had in lab sciences, where we go to the lab and do experiments and come up with products and everything, those principles can be borrowed and bring and introduce a large element, or at least help with reproducibility in AI systems. We can learn how to document our systems like people do in actual labs, the processes, the steps, the choices, the configurations, and their decisions. Then we can have some reproducibility. We can have the chance of having, to a large extent, reproducible systems when it comes to AI. So this is the challenge we have today. So, like I said earlier, I love solutions. I love to think about solutions. I started by saying this, that I think reproducibility is an engineering problem. So I'm not going to leave you without a solution. I think reproducibility should be an engineering requirement. When we're designing models, when we're working with AI systems, it should not just be an afterthought or some sort of documentation exercise. Like, you do the process and then you can do that. And this is something we implement today in our different works that we do. I'm not going to mention where, but in the different works that we do, this is something we are very keen on. First of all, there has to be logging. It's non-compromisable. Everything needs to be logged. There has to be versioning. This was the data. This is the version of the data. These are the people who accepted it. This is how it was changed. Everything. So that traceability element is essential. It cannot be changed. And the system design as well. So if you approach these from an engineering process, from an engineering perspective, then you do stand a fair chance of actually reproducing AI systems, AI workflows. So let's start with the basics. In your experiments, in your designs, are we logging? Are we versioning? Are we adding some traceability? There's so many tools to help you with this, right? I love weights and biases. It's amazing for reproducibility. Helps me track every experiment that I'm doing, what I'm changing in a model, what's happening when I change that model. It tracks the data and all that kind of thing. So super important again. You cannot skip that part, right? And so that's what I'm saying. Like, I think we can, to a large extent, solve reproducibility with engineering, embed this issue in engineering. Once you log, my supervisor was, again, very adamant on logging. And whenever I would delete something, I would run some experiment and I would look at results and I was like, these results are not good. So I would delete them. And he would get really, really mad at me for that. It was like, we never delete a result. You always put it, you log it, you write why it was that, and you put it somewhere, because you never delete a result. So I learned this the hard way, to kind of be very careful about some of these things. So I log my experiments. I make sure that every data that I'm interacting with is really well versioned. And there is a traceability. I know who accessed this data where. And again, you can do that with a lot of tools out there, including weights and biases and whatnot, and with system design. So what I'm saying is that for us to truly have a possibility of reproducibility, it must be engineered into our workflows. It must be there from day one. Like, we're designing this with that in mind. And so what we call open workflows, and I know people have different definitions and versions of this. I'm going to give you my own understanding and my own meaning of what open workflow means, which is basically what I was talking about earlier. Open workflows as an engineering infrastructure. So open workflows, for me, my understanding of it is systems where every step can be seen, traced, and reconstructed. When I used to belong to the department called Department of Workflows and Distributed Computing, and we would do all these workflows. We were very keen on workflows and that kind of thing. So I really love the word workflows. And I'm thinking, open workflows, yes. Workflows is just a series of steps, like this happens, and then this happens, and this happens. And if you want to make them open, then the systems, everything should be seen, traced, and reconstructed. So what that means, it's making pipelines observable, right? When we run a pipeline, whether it's a pipeline to fetch data, whether it's a pipeline to train this model with this particular data, or it's a pipeline to run this evaluation benchmark, it needs to be observable. Making decisions explicit and making systems auditable, right? If you work in critical domains like healthcare or aviation and whatnot, these things come in really, really handy. So open workflows, for me, what it really means is version datasets. I'm very keen on this. Logged experiments, every experiment is being logged, transparent pre-processing with very good explanation on why this happened, documented prompts, and reproducible evaluation. I should be able to run your benchmark and come up closely with a similar answer. Why? Because I mean, all the other domains we can do this, right? You can run a benchmark of a hardware, and unless things are so drastically different, you will end up with a very similar experiment. So I see open workflows as an engineering infrastructure to help us achieve reproducibility. So what's the practical? I said I'm not going to leave you dry and hanging. I have some perspectives and thoughts on this. So a reproducible workflow for me should include these things at minimum. Some data snapshots and some access protocol so that we can trace that. You can't really say you're doing reproducible work if you're not versioning your code. And I see this a lot with scientists. Sorry to blame you guys, but scientists will just do a lot of their work on their repository and then make just one push in a month. And that's not really how we want things to be, right? We want to be able to see the versioning and what changed this week and what changed next week, and so that we can have a good lineage and a good history of what really changed. Environment specification, luckily now with better compute infrastructure, we're able to solve this problem of environment. Nowadays, you ship a model with the whole environment on how to do it, right? Containerization has really helped on that front, right? Model versioning and references, and then inference logs, the inputs, the settings that were made for that particular inference, and the evaluation pipelines and metrics. This is what I think is the bare minimum that we need. That being said, I am very pragmatic and very aware that it's not always possible to achieve full reproducibility, because sometimes you're using closed models. Nowadays, there's so many open source models, but we don't know the data behind them. We don't know some of the work that happened behind the scenes and all that kind of thing. And also some models are closed, right? We only have the inference engine. We don't really have access to the weights and all that kind of thing. So it's quite complicated. The data can be hidden, and this sometimes is by default, right? For privacy, for a lot of other reasons. But sometimes the data is hidden and systems keep evolving, so we can't always reproduce. However, we can still aim for minimums, like having maximum transparency, like I was talking about earlier, very good documentation and reproducible evaluation. That, I believe, is some sort of bare minimum. And why this matters is because, as my supervisor used to say, and most of these are his words, if it cannot be reproduced, it cannot be verified, it cannot be trusted, and it should not be used. So when reproducibility fails, especially in critical domains, errors don't stay isolated. I put this domino effect to show you that one error somewhere can just trickle down all the way to something else. And these were some of the hard lessons I learned in my master's when we were looking at fault tolerance. And that's why I started with that question of fault tolerance, that when a bit flips in a CPU, if you're typing your Word document, you're good. But if a bit flips in a CPU and you're flying a huge plane, those errors propagate really, really quickly, and you end up with a really big mess towards the end. So in conclusion, I love that AI is accelerating research and discovery. But without reproducibility, we have a huge risk of accelerating that error. And reproducibility is the only way we can keep science and systems honest. So again, in science and in a lot of other domains, reproducibility is the foundation of trust. And I would just like to stop here for now. Thank you very much.
Thank you very much, Albert. That was really, really impressive presentation. Personally, I really enjoyed. I liked your slides very much. Very simple, very clear, and I mean, you could see even the emojis. I mean, I hope everybody followed every bit of your presentation, and it was quite an informative presentation as well. Yeah, do we have any questions from the audience?
I have a
Albert,
hard
you
stop
have
at the end of the hour, so I've just
at
left
the end of the
10 minutes for questions. Yes.
okay, yes. So any questions from the audience? Precious, do you have any in the Etherpad? No? Yes, maybe.
Happy to hear your comments also. Maybe we have different opinions on what reproducibility means. I'm happy to be challenged. I'm happy to change my mind. Yeah.
No, actually, I like the fact that you stressed on the point of versioning. I mean, the steps or to get to reproducibility. Someone might say it might look not realistic, especially on an AI, but as you mentioned, it has to be intentional. So
Yeah.
that was really, really solid from a presentation. There's someone who wanted to say something. Yes, Agnes.
Yes, thank you, Albert. Sorry, I'm in a very, my background is not, it's not the
No
best.
worries.
Friday actually, pre-Eid afternoon, but very exciting talk. Thank you, Albert, for that. And I think bringing this new perspective, or the engineer's hat of
That one is quite a lot, yes.
it's really interesting. And I think for me, what I wanted to find out in terms of really moving this forward, as you know, in Africa, most of our AI models will probably stop at, that model development phase. They go up again. AI tool development, they go once in a while to the, evaluation of the product. And then for those that manage to go all the way up to scaling, they go up their scale. That probably takes them up. Sometimes the depth of how verifiable or trusted the tool is. So how do you think we can move this movement of ensuring reproducibility, oh God, in the AI tool development ecosystem in Africa? What do we need to do? Do we tackle this in the AI startups? Do we embed it when we're, developing courses around data science? How do we this point where we see it similar to drug development? You cannot get your drug to the market if you've not passed levels of tests. And how do we shift that needle to reality?
I think that's a very big question, but also a very important question and worth research, because it's not just Africa that we are struggling with these things, right? Even in Europe, in the US, well, US is the Wild West, so I'm not going to go so much into the US. But in Europe, for instance, they're having this complicated issue of verification, right? They have to deal with that now, right? If you put a model out there and it makes a particular decision or says something, if you were to go to a court of law, they need to sort of be able to come back to the decision and why it was made and that kind of thing, right? So they are really facing that problem, and they have to make sure that their AI is explainable and reproducible, and they're deeply embedding that. And I think part of the reason why they're doing that is because there are all these legal implications that come with that, right? So Europe, as you know, is goes crazy with regulation and laws and that kind of thing. And I think I'm not, as a Kenyan, I'm naturally rebellious, so I'm not very fan of putting so many rules on things. But I do feel like that's an important aspect on things, right? We model owners, model creators, or AI system creators, AI system designers need to be held accountable to some degree about the tools they put out there. So what do I say? If a case ends up in the High Court or in one of the courts in Kenya, the people behind a system that made a particular decision should sort of be able to show us how that happened, right? We shouldn't be okay with saying it's AI that decided, right? At least that's what I feel. So to answer your question, yes, of course, a lot of training, but also maybe from a policy slash, a legal perspective, right? Like, let's ensure that we use models that make decisions, whether it's if a bank denies me credit and they cannot tell me why they denied me credit, I would absolutely consider that discrimination, and I think people should be taken to court for that, right? You cannot tell me you denied your credit because I don't know our AI model said you're a risk, you know. So those are some of the things that I'm thinking about here. So my answer to that is approach it from legal and also from just like enforcing this idea that systems need to be explainable. It cannot always be a black box. I don't know if that makes clear. Yeah.
Yes. Good. So there's a thumbs up already. Yeah. So there's one more question from David, and then we can conclude.
Okay.
David, go ahead. No.
Thank you, Michael, and thank you, Albert, for the nice presentation. My question is on cost monitoring. Is it a good idea to have it as part of the reproducibility process in terms of monitoring the costs, especially currently we are using these paid versions of AI in terms of doing various experiments. Is it a good idea to also track the cost? Thanks.
You mean the cost of the tokens or that kind of thing?
Costs generally, tokens, for example, latency, all that tracking.
Oh yeah, absolutely. We are actually doing that in the different projects that I'm involved in, right? That's obviously very, very tracked. We both historical and like for everything that is being done, it's actually being tracked and traced already. I'm not particularly sure, like I've not really gone deep into that area, so I'm not gonna lie. I'm not particularly sure how that will eventually feed back into some of the critical issues that might be raised, but I do know for sure that that is being traced. Yeah.
Okay, thank you.
Okay. Maybe last one from Domin. Yeah.
Okay, thank you, Michael. I have a very
Yes.
simple question. Do you think software developers should also try and maybe involve the
Yes.
in their normal CI/CD pipeline, like the normal work they do every day? Is it important, the AI development for the software developer?
I think we have a lot to learn from software because software guys have been doing reproducibility for the longest time ever. I think they from this side of things, they sort of invented that, right? From Git to everything. They are very keen on reproducibility. And that's one of the things I like about software design because software in general is very reproducible, right? It's very deterministic, it's very reproducible, and all that kind of thing. So in fact, the other question should be, should AI engineers and AI developers be learning a lot from traditional software engineers, because those are the guys who mastered reproducibility from very, very early in the days. That's how I say this. I think software engineers are very, very good at reproducibility.
Yep.
Okay, thank you.
Okay.
There was one from Osman. I don't know if okay, there is one Precious. This is from chat, right?
Yeah.
Okay, so I don't know if we take it now or we can email this or add it on Etherpad so that we
There's
can.
one question. I can take one. I think we have 4 minutes left, so okay.
Yeah, so there is one in the chat. Reproducibility is very important, but in my opinion, it represents additional work on top of the usual tasks, into bracket data, quality C. This may be one of the reasons why data professionals are not always motivated to do it. Should there be dedicated roles for reproducibility, or should AI or data professionals handle these tasks themselves?
No, I personally think they have to handle that by themselves. And in as much as they try to run away from this, the good thing is thanks again to the software engineers. They're really good tools for that, right? Weights and biases does a fantastic job at, tracing experiments and that kind of thing. Git does a fantastic job at tracing your code and that kind of thing. We have really good tools for model versioning now. We have really good tools for data versioning. I think the AI community has realized this, and they've started making a lot of work around that. So yes, there is a lot of efforts and tools that facilitate reproducibility, thankfully. Yeah.
Perfect, Albert. Yeah, thanks. So I'd like to invite Miranda to just have 2 minutes to close this session, if that's okay, Albert.
Thank you.
Yeah, Miranda, the floor is yours. Thanks.
Yeah, thanks, Michael, and thanks, Albert. I was very proud to listen to you as a Kenyan, and I'm happy to know that you exist. So that was really, really interesting. And please do expect that we'll reach out to you just to have more discussions. But thank you so much for the perspectives on reproducibility as we knew it, and also thinking about it, especially now in this age of AI. The way you explained it was really clear, and it's a lot to think about even now as we are moving into this space and trying to navigate it. So we really appreciate you taking the time, and we look forward to having many more sessions. Because I have two of the PIs from DSWB, I would also like to kindly request Prof. Alemseged maybe to just close us out, and then we can be done. So, Prof, over to you. Thank you.
I think, all right. Yeah, and I think on behalf of the, in a noisy place, on behalf of specifically the and the organizers from OSPO, whoever's attended, and of course to you, Albert, thank you for the great session. We'll be banging on your door again to see a demo of some of these very important aspects of reproducibility, and we look forward to working with you and hope all the software engineers and data scientists will pick up and spread the gospel of what needs to be done to have trustworthy AI in Africa. So over to you, Michael, and thank you. Bye-bye.
Yeah, thank you. We're on top of the hour. Thanks, Albert.
Thank you very much. Appreciate it. Thank you.
Yeah, bye-bye.
Bye.